Hello everyone. In the previous module, we just started off with the dimensional similarity. Let us just take a quick look. So we just said that these are the non-dimensional numbers and we non-dimensionalized the continuity, momentum and the energy equation. Continuity led to no non-dimensional number. The momentum equation gave us Reynolds number and GR by Reynolds number. And the energy equation gave us 1 by Prandtl number and 1 by REH. So these were the non-dimensional numbers which gave, and if you see here, this is mass and momentum equation. You could solve in the forced convection separately and then solve energy equation. But as you can see, these three equations, U, V, T are all coupled. So you need to solve all of them together. That is, these are coupled equations. That is, simultaneously you need to solve in order to get U, V and T. So you have delta and delta T and Nusselt number coming from these solutions, which are nothing but functions of Rayleigh number, Reynolds number and Prandtl number. Already we have seen the scales of the Nusselt number is of the order of Rayleigh number to the power of 1 by 4 or Rayleigh into Prandtl number to the power of 1 by 4, depending whether the Prandtl number is greater than 1 or less than 1. So then we said that GR by RE squared less than 1 represents forced convection domination. Grashof number divided by Reynolds number squared greater than 1 represents natural convection domination. GR by RE squared is of the order of 1 represents that both natural and forced are of the same order. So then we represented these correlations. This was for the vertical plate, and till 10 to the power of 9 it is laminar, above 10 to the power of 9 it is turbulent, and this is the correlation which works both for laminar and turbulent. For an inclined plate, instead of G in Rayleigh number, I need to replace it by G cos theta. And this is a horizontal plate. As I said, 0.54 is the same as 0.59, and here 0.15 is the same as almost 0.1. So in fact, if it is turbulent, horizontal plate would be giving higher Nusselt number than the vertical plate. And for lower surface, that is, if the hot surface is bottom but the top surface is insulated, you get a Rayleigh number almost half of the other situation where the top surface is heated, that is 0.27 Rayleigh number to the power of 1 by 4. So these were the correlations for cylinder and sphere. Now this is the problem which we wanted to solve. So here it is, I don't think I am going to solve completely step by step, but I will just give you the glimpse. That is, this is length of 6 meter, long section of 8 centimeter diameter. So diameter is 8 centimeter and passes hot water pipe in the figure below, passes through a large room whose temperature is 20 degrees Celsius, that is T infinity equal to 20 degrees Celsius. And if the outer surface temperature of the pipe is 70 degrees Celsius, that is, which is maintained at 70 degrees Celsius, constant surface temperature boundary condition, determine the rate of the heat loss from the pipe by natural convection. What are the assumptions? Steady state, air is ideal gas, local atmospheric pressure is 1 atmosphere. With this, my film temperature is Ts plus T infinity by 2. If I do 70 plus 20 by 2, that is, I get 45 degrees Celsius. At this, my thermal conductivity is 0.02699 watt per meter Kelvin, and Prandtl number equal to 0.7241, and kinematic viscosity is 1.749 into 10 to the power of minus 5 meters squared per second, and beta you can take it as 1 by Tf, that is, in the absence of the, you can get from data, but this is because I am taking it as an ideal gas, so I can take it as 1 by 318 Kelvin. If you take 1 by Tf, you have to convert this into Kelvin, that is 45 plus 273 is going to fetch you 318, that is your Tf. So with this, you can calculate Rayleigh number as G beta delta T, that is Ts minus T infinity d cube upon alpha nu, or d cube into nu squared into Prandtl number. This is Grashof number into Prandtl number gets me Rayleigh number, because I have given the properties like that. If you substitute that, you are going to get the Rayleigh number as 1.869 into 10 to the power of 6 as our Rayleigh number. So if you come here and you see here Nusselt number correlation is 0.6 plus this whole of this equation. If you substitute this Rayleigh number in the Prandtl number of 0.7241, you are going to get the Nusselt number as 17.4. So what is H? Nusselt number equal to HD by K. H equal to 17.4 into K by D. If you substitute 8 centimeter is 8 into 10 to the power of minus 2 meters. If you substitute those 17.4 into 0.02699 upon D, that is 8 into 10 to the power of minus 2, you are going to get this as H as 5.869 watt per meter square degree Celsius. Please notice, most of the times if nothing is there for natural convection, we have been taking H as 10. So this is the number typically why we take 10, because it's around that. So you take surface area pi dl, you can calculate the surface area. So Q dot equal to HAS into Ts minus T infinity. You are going to get this as 443 watts. But now we have neglected radiation. Now you see radiation value. The main reason for solving this problem is to show that radiation is as important as natural convection in case of natural convection problems. So Q dot equal to sigma epsilon Ts to the power of 4 minus T infinity to the power of 4. Let me take epsilon as 1 and sigma is 5.67 into 10 to the power of minus 8. Ts has to be converted into Kelvin, so that is 70 plus 273 is Ts and T infinity is 293 Kelvin. If you substitute that, you get 553 watts. You see, Q dot natural convection was 443 watts, but Q dot radiation is 553 watts. So both are comparable. So generally, in case of course, if the epsilon is less, you can have radiation less, but nevertheless, they are comparable until and unless you consciously make the epsilon to 0.1 or less than that. So generally, whenever natural convection is important, radiation neglection has to be carefully done. That is the message, the takeaway message from this problem. That's the reason why I solved this problem. Now if you see the slides, this problem is about a vertical plate. I am not going to solve this problem. A room temperature has been given, surface temperature has been given. Similarly, you get the properties. And for vertical plate, the case is horizontal plate, the case is horizontal plate facing upwards, horizontal face facing downwards. You get Nusselt number for vertical plate 113 and horizontal plate, Q dot is 115. That is for Q dot vertical, you get 115 watts. Q dot horizontal facing upwards, you get, if you just see here, you take characteristic length surface area by perimeter, that is L by 4. If you just take that as your characteristic length, you get Q dot as 128.4 watts, and Q dot H facing downwards, you are going to get, if you see the slide, this is Nusselt number 0.27 Rayleigh to the power of 1 by 4, and you get Q dot as 64.2 watts. Remember, in all of this, the Rayleigh numbers are so low that they are all laminar, so corresponding correlations only I have taken. So you see, the horizontal facing upwards heat transfer is greater than that of the vertical. So that is the understanding what we get through problems when we do. So in assignments you will get few more problems. Now one final thing in the slides is you can have both mixed convection. So you can have forced convection and the natural convection, but sometimes it is assisting, that is forced convection and the natural convection currents are in the same direction. That is called assisted flow. If the natural convection and the forced convection currents are in the opposite direction, that is what is called as the opposing flow. So that is when you have combined, you generally take Nusselt number combined as Nusselt number forced plus or minus natural, Nusselt number natural, plus for assisted flow, minus for opposing flow, and this N would be depending on the geometry. For vertical surfaces, N happens to be 3. This I have not derived, without derivation, I have just stated it. Now let us take up very important thing, that is, we have done the scale analysis, we have gotten various things. Let us see how we can apply all this for real life cases. Let me take a simple vertical channel flow where the flow has been initiated only by natural convection. That is, I can have two situations, that is, if my plates are far apart and this plate is maintained at Ts, these two plates are maintained at Ts and the distance between these two plates is d, and the boundary layer grows. This is my natural convection boundary layer. That means one is not interacting with the other. So you have the temperature like this, and again you have the velocity. This is the velocity profile. Okay. So this is what is your velocity profile. So if you see the slide, if the figure is not clear, in the slides if the figure is clear, this is the velocity profile, this is the temperature, and this is height h. But on the other hand, if I have brought these two plates close enough such that the boundary layers just merge at the center, that is till they merge, it is entrance region, and after they merge you have fully developed region. I am considering the fully developed region, and the velocity profile would be something like this. This is the velocity profile. Please note slight difference. I am taking my coordinate x from the center and y as usual in this direction, and g is in the downward direction, and it is maintained at a constant temperature Ts, and the velocity u is in the x direction and the velocity v is in the y direction, and this is what I have taken. So how does the temperature distribution in the fully developed region look like? If I draw that, it will be more or less something like this, that is, because they are very close. So this is Ts and this is T infinity. Okay. So but in the entrance region, your temperature profile Ts would be very large compared to T infinity. So there will be a lot of temperature gradient. So this is T infinity and this is Ts. Now what is the objective? What is the objective? The objective is capability of this flow, to cool or heat the walls of the channel. What is the heat transfer rate? That's what we are getting by applying the fundamentals what we have studied so far. This is a kind of an application. So let's see how do we do it. So my continuity equation would be del u by del x plus del v by del y equal to 0, and as usual I will have only y momentum equation, there will be no x momentum equation. So you have u del v by del x plus v del v by del y equal to nu del squared v by del x squared plus g beta T minus T infinity, and this is what I get. But I have taken the channel long enough, so u is very small, u scale is very small, that is u is equal to 0 in the fully developed region. Is that? So if that is the case, this term will vanish. Now del v by del y in my this del u is 0, and also in the fully developed region del u by del x is 0 because velocity is invariant with x. So del u by del x is 0 in fully developed region. So that means del v by del y also is, which implies del v by del y is 0. So this del v by del y is also 0. So I get del squared V by del x squared equal to minus g beta by nu T minus T infinity. But now I need to actually take the energy equation to get this temperature, to solve it. That is U del T by del x plus V del T by del y equal to alpha del square T by del x square. I need to take this. But I will make an assumption, as I said, the temperature, as you can see here, it's almost closer to Ts. So I will take T, instead of solving for T, I will take T is equal to Ts, that is T minus T infinity as approximated as Ts minus T infinity in this equation. So then it will be only one unknown, that is d squared V by dx squared equal to minus g beta by nu Ts minus T infinity. Ts minus T infinity. So if we do that, Ts minus T infinity, so you get dV by dx equal to minus g beta by nu. I am integrating into Ts minus T infinity into x plus C1. Once again, if I integrate, V is equal to minus g beta by nu into Ts minus T infinity into x squared by 2 plus C1x plus C2. C1x plus C2. So, now what are the boundary conditions? Let's get back, because this is little tricky, because x I have taken at the center. So at x equal to 0, del V by del x equal to 0 because of the symmetry. So at x equal to 0, del V by del x equal to 0, and at x equal to d by 2, this dimension I have taken as d, that is d by 2, V equal to 0 because of no slip condition. So you have V equal to 0. So if you apply x equal to 0, x equal to 0, del V by del x equal to 0, if you apply from this equation, you can imply that C1 equal to 0. And in the second equation, if I, for this equation, V is equal to 0 minus g beta by nu into Ts minus T infinity into d squared by 8 plus C1 into d by 2. We have found C1 as 0, sorry, it would be plus C2 because C1 is 0, C1 is 0, so C2. So you get C2 as g beta by nu into Ts minus T infinity into d squared by 8. So if I substitute this, I get V equal to minus g beta by nu into Ts minus T infinity into x squared by 2 plus C1 is 0. So you get g beta by nu into Ts minus T infinity into d squared by 8. So you get V equal to g beta into Ts minus T infinity upon 8 nu into d squared if I take out common. So you get 1 minus of x squared upon d by 2 whole squared. D by 2 whole squared. So this is going to fetch you. So this is my velocity profile. But let me find out now, having this, now this is my plate, these are the two plates. Now let me take a small elemental length of dx, of width dx, not length, dx, from at a location x, and this is a Ts. Now what am I asking is, what is the mass flow rate which is flowing through this channel? So that is rho AV. Rho is going to be rho area is 2 into width, and I am going to integrate 0 to d by 2 v dx. Why 2? Because I am integrating 0 to 2 d by 2, whole channel means twice I have to multiply, because of the symmetry it is the same. So we I have the function as x rho into 2w 0 to d by 2 g beta ts minus t infinity into d squared upon 8 nu into 1 minus of x squared by d by 2 whole squared dx. Now I need to just do the integration, take out the constants out. So m dot equal to 2w rho g beta ts minus t infinity into d squared upon 8 nu into x minus of x cube by 3 into d by 2 whole squared within the limits 0 to d by 2. So you get 2w rho g ts minus t infinity into d squared upon 8 nu into d by 2 minus d by 6, that is d by 2 whole cube by d by 2 whole square, d by 2 by 3, so you get d by 6. So this is going to fetch me d by 3. So this is going to be 2w, 2 also becomes 4, so I can write w rho g ts minus t infinity d cube divided by, this is 4, 4 into 3, 12. 12 nu is my mass flow rate. Now the next thing to work out is the heat transfer rate, which is what is our objective. So the heat transfer rate q dot is equal to m dot Cp Ts minus T infinity. Already we have found m dot. All that I need to do is just substitute that. So I get q dot is equal to w rho g Cp Ts minus T infinity whole squared d cube upon 12 nu. But now let me find out Nusselt number for this. So the Nusselt number equal to heat flux upon Ts minus T infinity, this is h, into h upon k. What is heat flux? Q dot upon area, that is 2Wh into Ts minus T infinity into h by k. So that is q dot I have already found. So that is w rho g Cp into Ts minus T infinity squared into d cube upon 2Wh into Ts minus T infinity into k into 12 nu. Okay. So if you put all of that, so what is that I am getting? Nusselt number as g beta m dot Cp. Beta I have gotten missed out here, so sorry, beta in the subsequent steps has gotten missed out, so it is there, beta is there. So beta, g beta Ts minus T infinity d cube upon 24 nu, which is nothing but Rayleigh number upon 24. So you see, with that simple assumption we could get that for the flow to sustain, Nusselt number equal to Rayleigh number upon 24. So with this the module gets completed. In the next module we will think of stacking of plates. Thank you.